All right, this will be a video for group activity 9. I had to cancel class on Thursday because my back has been very bad, so I'm doing this by video as promised. Okay, so the first problem is this Rydberg equation associated with emission of light from a hydrogen, a sample of hydrogen that's very highly excited as the atoms give up their excess excitation and come down to the quote ground state. Different wavelengths of light are given off, which are just the wavelengths are characteristic of hydrogen itself. So if it were helium in there, the wavelengths would be different and the whole calculation would be different. Okay, for hydrogen, we can use this very simplified Rydberg equation. 1 over the wavelength is equal to R times 1 over N final squared minus 1 initial squared. And R is the Rydberg constant. Has the same symbol as the ideal gas constant, but it is not the same at all. It's equal to 1.097 times 10 to the 7 meters to the minus 1. So that's what has to be plugged in here. And then the way the problem is written, it's going to result from a transition that starts at some higher level and comes down to n equals 1. So that's going to be the n final. So it's going to end up at n equals 1. So 1 over 1 squared minus 1 over, and we're going to solve for this. So, the question is, what's the principal quantum number of the upper level? All right, and then you're also given the wavelength of light associated with the transition. So that is here, 9.50, 10 to the minus 8 meters. Now, sometimes this is given in nanometers. In this case, this would be 95 nanometers. And you absolutely have to convert it to meters because you have meters to the minus 1 here. And when we divide, those units have to cancel. So you got to have meters here. All right. So you're also given that it's in the ultraviolet. The ultraviolet means that it's n equals 1, which is also stated later in the thing. So, okay, so 1 over 9.50, 10 to the minus 8 meters is equal to 1.097, 10 to the 7 meters to the minus 1. And then this is going to be 1 over 1 squared minus 1 over n squared. We don't have to carry around the little I there for initial, just say n initial. All right, I strongly suggest that you divide both sides by 1.097, 10 to the 7 meters to the minus 1. So it's going to disappear on this side and it'll end up in the denominator on the left-hand side, as opposed to doing a distributive law multiplication thing. That just gets much more complicated. It's just much easier to do it this way. So 1 over 9.50 times 10 to the minus 8 meters. And then you're dividing, so it's 1.097, 10 to the 7 meters to the minus 1. This is equal to 1 over 1 squared, which is 1, and then minus 1 over n squared. Okay, so I'm going to say 1 divided by 9.5e negative 8 divided by 1.097 e to the 7, and this is going to be equal to 0.9596, 1 minus 1 over n squared. All right, next we are going to subtract 1 from both sides. So on the right hand side, 1 minus 1 is 0, so that goes away. 1 minus this is going to be equal to this minus 1, I should say. So it's minus 1 on both sides. So on the left-hand side, it'll be 0.9596 minus 1 is equal to negative 1 over n squared. All right, so on the left-hand side, you subtract 0.959, whoops, sorry, here, 1 minus 0.9596. So this is negative 0.0404, and then you have negative 1 over n squared. The next step is to get rid of these negative signs. They're positive, they cancel. And then you have 0.0404 is equal to 1 over n squared. So you want to put n squared on the left-hand side, and you can do so by multiplying both sides by n squared, and then you're going to divide both sides by 0.0404. Another way to think about it is these two are just going to switch places. So it'll be n squared is equal to 1 over 0.0404, and n squared then is equal to, this is 24.75. You can see that's going to round up to 25. So n squared is 25. Square root of both sides, n is going to be equal to 5. All right, so n equals 5. That means that hydrogen was excited all the way up to n equals 5. And it made a transition down to n equals 1. Doesn't matter what upper level it is, if it ends up in n equals 1, then that's going to be part of the ultraviolet spectrum, the ultraviolet transitions contained within that part of the spectrum, the ultraviolet spectrum. All right, so then number 2 is, about the quantum numbers. Give an example of an orbital that's represented by, so give an example of an orbital represented by n equals 3, comma L equals 2, comma M subscript L is equal to 2, and M subscript S is equal to 1/2. All right, now if you're actually looking at the group activity, this L is just typed lowercase l, and it looks like a 1, so that's very confusing. And then also the same thing here, it looks like a 1, but it's not, it's L, it's script L. I have some other versions of this group activity where I actually put the script in there, so I don't know where that version is. Anyway, okay, so let's see, an example of an orbital. So you want to know that the electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, etc. Okay, so it's just, I don't know where we're at with this, but this configuration, I don't know exactly where we stop for this particular example, but you need to keep that in mind. Okay. All right. Now, the other thing is that you can look at the symbols. So if n is 1, you can look at the examples. N equals 1, n equals 2, n equals 3. So these are going to be the main levels, main energy levels. So this is described as the principal quantum number. So these correspond to the numbers here. 1, 2, 2, 3, 3. Those stand for the principal quantum number, which in the old version of quantum, before quantum mechanics was established, classical mechanics, you had levels 1, 2, and 3, or orbits 1, 2, and 3. So each one of these orbits is numbered, and that corresponds to n as well. So n equals 1, n equals 2, n equals 3. Now with quantum mechanics, we have these different energy levels, and we have the same labels, like that. All right, so then n equals 3, that's certainly fine. Now within the rules of the quantum numbers, you can generate what the allowed or possible values of L and M sub L are, and so on. So, for example, if n equals 1, L can be equal to 0, comma, all the way up to n minus 1. All right, so in this, and then, so for, all right, we'll stick with that. Let's keep going. If n equals 2, L can be 0, comma, 1, all the way up to the value of n minus 1. So if n is 2, it can only go up to 1. So I'm giving you sort of the general thing here. But for n equals 1, it can only be L equals 0. For n equals 2, it can only be 0 and 1 because it goes up to n minus 1. All right, so then let's just do one more here. If n equals 3, L can be 0, 1, or 2, but not higher than that because 2 is n minus 1, right? So, you know, we finished that part right there. Okay, so then you have those. Now they have names, and for L equals 0, this is an s orbital. For L equals 0, it's an s, and then L equals 1, it's the p, not orbitals, subshells. And then here you can have s, p, and d subshells. Okay, and then within the subshells, you can have the orbital designation. So in this example, is it possible if n equals 3, is it possible to have L equals 2? Yes, it's right here. So this tells us that this orbital is going to be a 3D. Okay, it's a 3D if it has n equals 3 and L equals 2. Okay, so we're looking at a 3D orbital. And then you have your m sub L values. Actually, up to this point, it's just, we know that it's the 3D subshell. Okay, now let's look at the orbitals. So let's do this again. N equals 3 is a good example here, so let's just kind of continue with that. So if n equals 3, L can be equal to 0, 1, or 2. Okay, and then you can write them out. So L equals 0, give it some space, 1, give it some space, and 2. Okay, those are the subshells. Then M sub L, subscript L, tells us the different orbitals that are within each subshell. So with, let's start with 2 over here. You can write 2 and negative 2, and then you want integer values in between. So this would be negative 2, negative 1, 0, 1, and 2. For L equals 1, similarly, you take 1 and negative 1. So negative 1, and then you want integer values in between. So you can just generate this. I started on the 2 because for L, when you say L equals 0, M sub L equals 0, it doesn't really make a lot of sense. Without a little perspective there. All right, so then these are the orbitals. Those are the quantum numbers for the orbitals, but they also have names. So those names, this is going to be the s orbital. This is going to be, it doesn't matter if it's negative 1 or positive 1, goes for it. The order of it doesn't matter. But you got px, comma, py, and pz. Those would be the names associated with those numbers. And then for the D's over here, remember this is S, P, and D subshells. So for the D's, you've got here, and again, the order doesn't matter. dxy, dxz, dyz, dx squared minus y squared, and dz squared. So there's 5 orbitals, and I guess we can put commas in between them. There's 5 orbitals associated with n equals 3. All right, so then you go back and look at the question again. Give an example of an orbital that's represented by n equals 3, L equals 2, and then M sub L is equal to 2, all right? And M sub S is a half. That's just the spin part of it. So you could say n equals 3, L equals 2, which makes it D. M sub L is equal to 2 as well, so that makes it a D subshell. And what's the name of the orbital? You can pick any one of those 5. Let's call it the DYZ. DYZ orbital. You can pick any one. They're all the same. So this would be the principal quantum number here. All right, so then it would be, the complete name for it would be 3DYZ. All right, and then the last part is the spin. It says in this case M sub S. So M subscript S is 1/2. It can be either a half or a negative a half. You can think about the electron kind of spinning on its own axis, and it's either spinning in this direction or it's spinning in this direction, clockwise and counterclockwise. That's another way to say it. In terms of numbers that are associated with the magnetic fields, you'd say maybe this one is 1, MS is 1/2, and MS is negative 1/2, meaning they're spinning in the opposite directions. It really has to do with the magnetic moment that is generated perpendicular to this electron that's spinning, and whether that magnetic moment, that magnetic field, is either associated with or against the external field of the other electrons in the atom. Complicated, don't worry about it. And just pick one, doesn't matter. So this would be the complete designation for that orbital, for the electron. Yeah, it's one electron you've chosen. By the time you've chosen MS is 1/2, you picked one of the 2 that can fit into that orbital or be characterized by that orbital. So, you know, MS 1/2 means spinning clockwise or counterclockwise. It doesn't really matter how you do it. But anyway, that would be the answer to that. 3DYZ would be the answer for that one. All right, now the third question is, what is wrong with the following designation? N equals 3, L equals 3, M sub L is equal to 2, and M subscript S is 1/2. So the answer is that this is not correct. So remember, the rules are that L is equal to 0, 1, all the way up to n minus 1, n minus 1. And n is 3, right? So L is 0, 1, all the way up to 3 minus 1, which is 2. So it can only be 0, 1, and 2, which is S, P, and D subshells. So can L be 3? No, it can only go as high as 2 if n equals 3. So this is the one that's incorrect. If you have L equals 2, certainly you could have M sub L value 2 as well, because you can have 2, 1, 0, negative 1, and negative 2. So that's the issue, is the second one, the L quantum number. All right, now we want to give the electron configuration of phosphorus for number 4. All right, 4. Electron configuration of phosphorus. And let's see here. So phosphorus is element 15, so P15, and it has 15 electrons. So you just gotta put them into the orbital configuration, which is 1s2, 2s2, 2p6, 3s2. How are we doing? We have 2 plus 2 is 4, plus 6 is 10, plus 2 more is 12. We're going to 15. So the next one would be 3p3. Okay. That is what I gave you in the key, but we can also, this is the electron configuration. Whoops. All right, next would be, didn't ask for it, but we can do it anyway. The next thing would be the orbital diagram. So that'll give information about the energies associated with each one of the orbitals. So you have 1s being lowest in energy. The next one, this is an energy diagram here. 2s is next lowest in energy. After that, you get the 3p orbitals. They all have the same energy going, so they're all listed, given at the same position on the energy graph. So you have px, py, pz represented for each one of those horizontal lines. Then 3s, and then 1, 2, 3, 3p. So, you know, if they were all lined up, you would see it's 1s, 2s, 2p, 3s, 3p, you know, energy increasing each time, but they're kind of separated into s's and p's and d's if those are included as well. Just gives a little bit more clarity, and each one of those subshells has slightly different energy if the atom has more than one electron. All right, so then we're going to put the electrons in, and the first two electrons fill into the 1s. So you have n equals 1, L equals 0, M sub L equals 0. This first one is M sub S is 1/2. The next one is M sub S is all the same, but it's -1/2. So let me write that down. So for what I just said, you got N equals 1, L equals 0, M sub L is equal to 0, and M sub S is equal to 1/2. The next electron that fills into the same orbital, that has the same energy and the same characteristics, but the spin is opposite. So N equals 1, L equals 0, M sub L equals 0, M sub S is equal to -1/2. So you have +1/2, -1/2. Otherwise, the characteristics of these two electrons are the same. And with opposite spins, they kind of fit nicely together into that 1s description and system. All right, 2s similarly is like that. Then you have Hund's rule, which deals with when you have more than one orbital that has the same energy, or you could say when you're filling a subshell when you're going across. So this is px, this one is py, and this one is pz. So Hund's rule is that it fills across 1, 2, 3, all spins pointing in the same direction. Then you come back 4, 5, 6. All right, so far we have 2, 4, 6, 8, 10. We have 5 more to go. The next two go over here. So there's spin up, spin down in the 3s. And then this 3p, let me move these up just a little bit. 1, 2, 3. Those are the 3p's. You have 3 more. 1, 2, 3. So they fill across with spins parallel, and that is what phosphorus is like, neutral phosphorus. Now, phosphorus is just like nitrogen. It's directly underneath it in the periodic table. It's in the same group, but it's the next one down. And it's the same with nitrogen, where you have 3 unpaired electrons, but it's happening in here because there's not as many electrons, right? Okay, so then let's see, that I'm giving you more information than what was asked for. All you had to do was give the electron configuration, but now I've given you the orbital diagram as well. And now let me end that with the orbit diagram. Okay, so the orbit diagram is the circles, the old classical idea that the electron goes around the nucleus. And you have n equals 1, n equals 2, n equals 3. That correlates with the principal quantum number. So you got 2 electrons that are going to fit in n equals 1. You have a total of 8 electrons that are going to fit in n equals 2. So in this orbit diagram, you're not differentiating between s's and p's, right? They're just 8 of them. 3, 4, 5, 6, 7, 8. And it's something simple like hydrogen. No, that's not a good example. You just assume that the interactions between them are minimum, and they're minimal, and so it would end up that you could fill them together, the same main energy level basically. No difference between the S's and the P's. It's not really true, but for this diagram, it's okay. Then for n equals 3, there's just this part right here. So there's just 3 of them. Okay, it would like to be 8, so it's going to give up those 3 electrons in order to have an 8 is in n equals 2 as the final state for n3 minus, nope, I didn't mean to say that, for p3 minus. If it's lost 3 electrons, then it's the ones on the outside here that will be lost. Okay, all right, that's not what the problem asked you for, but I gave it to you anyway so that you know the difference between the electron configuration, the orbital diagram, and the orbit diagram. Okay. All right, now the next question is draw the orbital diagram for the valence shell of copper. Okay, so copper, that is number 4, is that right? 4. Oh, there's 2 number 3s, how can that be? Yep, there's 2 number 3s, okay. So for then, orbital diagram, for the valence shell of copper. All right, now if you look in the periodic table, you know how you've got these sections, right? And we're talking about this element and this element. You have copper and chromium. So this one is chromium, this one is copper. And these are the 2 exceptions to the filling of the electrons into the electron configuration. So they tend to grab electrons from 4s and put them into the 3d in order to achieve stability. And there are others. If you looked in the periodic table, with the, there's one posted on our Canvas page, which gives you the electron, for each element gives you the electron configuration of the outer shell. It's a pretty nice periodic table. Check it out. And what you'll see is that if you go down the group for either chromium or copper, that you'll see these same exceptions for the elements further down. Okay, so chromium has 24 electrons, copper has 29 electrons, and so we're after copper, which is this one, 29 electrons. All right, so then you have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Okay, I went through that pretty fast, but you can add it up. 2, 4, 10, 12, 18, 20, 29. And this last part here, you know, if you look at the periodic table, you'll see there's a correlation in the 9, that it's in the 9th position in this block. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That would be, you know, what you would pull from the table, but it turns out that it's not correct. So anyway, first of all, it's asking for the orbital diagram for the valence shell of copper. This is it right here. That's what it's asking for, 4s2, 3d9. But we haven't done the correction yet. But anyway, that's the valence shell right there. So what happens is that one of the electrons in the S gets promoted, get a little bit more energy to put it into the 3D subshell. And then there's stability associated with it, which kind of compensates for the energy needed to promote it into that state or into that orbital. So this is actually incorrect. Instead, you have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. So this is what the question is after right here, 4s1, 3d10. Now, if you were going to do the, let's see, the orbital diagram, which it did not ask for, it would be 1s, 2s, 2p, 3s, 3p, 4s, 1, 2, 3, 4, 5, 3d. So I go over this in my my lecture video as to why these energy levels, you know, are different than what you would expect. You'd think, for example, 3s, 3p, 3d should all have the same energy, or at least they should increase that way. But the 4s2 is actually lower in energy. Anyway, so you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Okay, so you really see a lot if you write out this orbital diagram, because why was it necessary to bring this electron over here? And that's because there's stability associated with this. In this case, it's a filled shell. In the case of copper, you see chromium, you see the same thing going on, but you end up with 5 electrons going across. So that's the half-filled shell. There's stability associated with that as well. All right, so then the next one is, which has greater ionization energy, nitrogen or oxygen? And for that, on your Canvas page, I have a slide. I have a link in the section on the tables for the ionization energy. And I'm going to go look at it right now myself. So hold on. It's in the section under useful tables for quizzes and exams. You have the ionization energy graph. And I'll draw a little bit of it here. Okay, so this is ionization energy versus atomic number. And you have some energy numbers. I'm not concerned with the numbers. Hydrogen, this is going to be 1. 1 for hydrogen, has some certain amount of energy. And then helium is up here, has its higher ionization energy. The ionization energy is the energy needed to completely remove an electron from a neutral gaseous atom. So you have neutral gaseous hydrogen. How much energy does it take to pull off the electron? And the number is somewhere around 1,300 kilojoules per mole. For helium, it's higher. It's about 2,200. So that's what you're seeing here. The amount of energy needed to remove an electron, that's the ionization energy. Then that's helium. Then it drops down to, we have lithium. The next one is beryllium here. It drops down for boron and then shoots back up for carbon. This is that one right there, beryllium. Carbon, and then the next one is nitrogen. Then it drops down for oxygen and then comes back up for fluorine, and then neon, like that, something like that. Okay, and then it happens again, shoots down and then zigzags back up, shoots down, zigzags back up. Okay, so the question is, let's see, which has a greater ionization energy, nitrogen or oxygen? You can see from the table that nitrogen has a greater ionization energy than oxygen, right? Oxygen's just a little bit lower. But going across the period, you have lithium, you have beryllium, then you've got boron on the right, carbon, nitrogen, oxygen, fluorine, and neon. So the trend is that the size decreases going from left to right, and that the ionization energy increases going from left to right. So you should see, each number getting higher than the next one going across the period, right? But you don't. For some reason, nitrogen is higher than oxygen, and you would expect it to be the opposite. And it has to do with the electron configuration, the fact that nitrogen has a half-filled shell, and that's the same concept that was in the last one. So nitrogen has 7 electrons, configuration 1s2, 2s2, 2p. That's 4, and it's going to have 3 more. It's electron configuration. The orbital diagram, 1s, 2s, and 2p. So you have 1, 2, 3, 4, 5, 6, 7. The fact that this is a half-filled shell, again, shows stability, and it is more stable, and so it's harder to ionize it because it's more stable than oxygen. So oxygen, of course, would have 1 more electron in here. It creates instability relative to the stability of nitrogen. Okay, so that's the answer on that one, that nitrogen has higher ionization energy. All right, now the size is related, as I said before. The concept here is that as the size decreases going from left to right across the period, now the electrons are closer to the nucleus here as opposed to here, right? So I'm saying in the little small one, the outer electrons are closer to the nucleus than they are here with the bigger ones. So as the size decreases, it turns out it's easier to harder to ionize the ones closer to the nucleus. So the ones further to the right, which would be fluorine and neon, those are harder to ionize. So it takes more ionization energy to knock the electrons out of those because they're held more tightly. That's the idea. All right, so then this question was, okay, so size is related to ionization energy. No, number 6 just has to do with sizes in general. So the question is, what's bigger, beryllium or barium? So which one is larger, beryllium or, what was it? Beryllium or barium. Okay, so the other thing about the size is that if it's in the same group, so you have beryllium, this group 2, magnesium, calcium, strontium, barium, like that. So size increases going down the group, and you got electrons that are filling out into the outer subshell, or outer shells, I should say, if they're associated with the higher number of electrons in the configuration. So the one further down in the group is the one that's going to be larger, and so in that case it's going to be barium. That would be the answer to that one. Then which has a greater size, N3 minus or N neutral? So which has a greater size? N3 minus or N? Okay, that's another question related to all of this. And nitrogen neutral has 7 electrons. N3 minus, you've added 3 electrons, and N3 minus, that's going to be 10 electrons. I think I had a mistake. Where was that? got a mistake right here. I was saying electrons being removed. That's going to be, let me go back to this point here. I definitely had a mistake on that. Phosphorus 3 minus. It's just like nitrogen 3 minus, so that means it wants to add 3. So there's a mistake on that phosphorus. I'll go back to it. Okay, so anyway, you have 1s2, 2s2, 2p3. And if you've added 3 more to it to make 10, you have 1s2, 2s2, 2p6. So which has a greater size? In this one, go back to that shell model. So you have nitrogen, you got the first 2 are in n equals 1, and then you've got 5 more in n equals 2. So 1, 2, 3, 4, 5, like that. And that would be nitrogen. Then you've got, you're not filling into another shell, just putting more into the same shell. So N3 minus is going to be, 3 minus. N3 minus, let's see, 1, 2, and then you've got 8 of them in n equals 2. 1, 2, 3, 4, 5, 6, 7, 8. So 3 minus is what nitrogen wants to fill its shell to make 8. And, oh, I know the mistake I was talking about. To get 8, you're combining 6 and 2. Okay, so it does want 3 minus. And then, but the difference is that both of these drawings are associated with nitrogen, which because it's atomic number 7, it's got 7 positive protons in both, right? They're both nitrogen, so they both have 7 protons. So in this case, you've got 7 protons and 7 electrons. You could say that's kind of electrically neutral. In this case, you've got 7 protons and 10 electrons. It's the extra 3 that are causing havoc here when they try to fill into this n equals 2 shell. There's no increase in the number of positive charges to kind of balance it, and so they tend to repel each other. There's a repulsion interaction between these extra electrons and the other ones, so to speak. And so it tends to kind of expand it. There's an expansion associated with repulsion. So this is an example where the size increases even though the number of protons is the same. So this one's going to be larger and this one will be smaller. And let me go back up to phosphorus. What the heck was I talking about? Phosphorus has 15 electrons, and the configuration is 1s2, 2s2, 2p6, 3s2, 3p6, and then p3 minus has 18 electrons, 1s2, 2s2, 2p6, 3s2. This is a mistake here. That should be a 3. Going too fast here. Okay, 3p3. So we got 2, 4, 10, 12, 15. And then for the case of p3 minus, 3s2, 3p6. So it's just similar to what happened with nitrogen, except you've got some additional electrons in n equals 3. And I feel like I said something wrong back then. Yeah. How many electrons phosphorus has? 15. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, yeah, this part was wrong. So there's 10 and 5 is 15. Then if you add 3 more, I'll make those blue. You're going to have 1, 2, 3. Is that right now? You got 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's how you do it. All right, so these should have been green because that's the proper orbit diagram. And then if you're making P3 minus, the blue ones, you want to add those in. And then you get 5 and 3 is 8. So the reason why phosphorus wants to be 3 minus is that it can form the octet. All right, so that is the story there. Okay, that's the end of this. Now you can watch this, and when we meet on Tuesday, you can ask me to go over this again. I was pretty fast there, but I think I got all the parts to it. And but I agree that this is not easy stuff. Just some simple ideas like the relationship between N, L, and M sub L. That stuff's very crazy if you've never seen it before. It just takes a long time to let it all settle in your brain. You see how all the parts of it come together into a really interesting picture. So, okay, that's it for now. And study hard. Test is coming up soon, and I'm going to open it for you and have that ready for you on Tuesday. Well, the test is Thursday, but I'll have it ready on Tuesday. And email me if you want me to do anything else. We'll just do some last minute review on Tuesday. And that's about it. Okay, thanks. Have a good weekend.